All right, so what we're going to try to do now is using our definition of energy, we need to figure out how much velocity we have to have, initial velocity we have, to get it away from the Earth. In fact, we want to get to a velocity. Our velocity can be zero, but we want it to be zero at an infinite distance. So what we're going to do is our energy initial equals energy final. So we're going to have our gravitational potential plus our kinetic initial has to be gravitational potential final plus kinetic energy final. Okay? So we're just typical conservation of energy. Our gravitational potential initial is this one, which is minus g mass of the Earth times the mass of your rocket divided by the radius of the Earth, because that's where you're starting from. Plus 1/2 mv initial squared. But what's your final? Your final is where r goes to infinity, but we just said at r and infinity, your gravitational potential goes to 0. And we also said that we want to get away from the Earth, so if you're at an infinite distance away from the Earth, your velocity can go to 0 as well when you're at an infinite distance. So you could be slowing down, but in an infinite distance, you finally would coast to 0. So this side of the equation just becomes 0. So we're just going to solve this, what velocity you need. This is technically called the escape velocity, because that's the velocity you need to escape from that gravitational potential. So we're going to put this in, I'm going to move this to the other side, so we're going to have 1/2 mv escape, I'm going to call it the escape velocity squared, and then go gmem over the radius of the Earth. So I just move that to the other side. Now I'm going to solve for this. Notice that the mass of the rocket is irrelevant. It goes away. I'm going to put the 2 over there and take the square root. I'm going to get the square root of 2g me over the radius of the Earth. That's how fast you have to get a rocket going to escape the gravitational potential of the Earth. If you're going to the moon, you've got to get this velocity. If you're just going to the space station, you don't. You have to get this velocity because it's in circular orbit. What's the difference between that and that? Well, look, they're GME over R, but the 2. So the escape velocity is the square root of 2 times greater than the circular orbit velocity, or what we call the minimum energy velocity. So you have to increase it by, remember the square root of 2 is about 1.41. You got to increase by about 40% your velocity to go from circular orbit to get enough energy to go to the moon or to get away from the Earth. Or you just go this fast right to begin with, and then you just keep going. So objects, all the ones that they sent to Mars, all the probes to Mars and to Jupiter and to Saturn, they've all had to reach that velocity. Now, when they sent the astronauts to the moon, what they did first is, here's the Earth, they put them in orbit, and then they had another rocket on the rocket, so huge rocket, these Saturn V rockets, just to get the command module up into space, and then they fired its rocket to give it an extra velocity so it could go to the moon, and then circle, then it would go circle into orbit around the moon, then they fired the rocket and came back. So they did it in stages. They went first this velocity, get in orbit, then from here to get to the moon. Then they actually slowed down, so they go into lunar orbit, and they sped up again to come back. So that's how they made the, how they went to the moon. I find that nowadays people don't realize that they didn't grow up during the moon launches, and they think, oh, they just launched and went to the moon and came back. Well, no, there were actually multiple stages to getting to the moon. And they're looking at putting men back on the moon again. And they're even trying in a few years, and they have rockets that they're testing right now to do that. And they'll do a similar type thing. All the details haven't been worked out, but they're looking at maybe 2024. That's their timeline. I've known with space stations and everything else, their timelines are usually never anywhere close. Meaning they say 2024, maybe by 2028, 2029, there'll be somebody going to the moon, but who knows? All right, so these things you need to know. You also need to understand this. This you should already know, but you need to understand that because that's what you have to use for gravitational potential for any object orbiting out in space. All right. Now, let's do, remember this one over here. Remember, this is velocity for a circular orbit. So what's the total energy in a circular orbit? Circular orbit. Well, remember your total energy is just equal to your kinetic energy plus your potential energy. So if an object, let's have it orbiting the Earth, going a circular orbit around the Earth, we say that the total energy is equal to 1/2 mv squared minus g m me over re. Sorry, put that backwards. Me is the big M. So this is, little m is the mass of the satellite going around. And big M is the mass of the Earth over the radius, not the radius of the Earth, sorry. This is the radius of the orbit. So that's the distance from the center of the Earth to the satellite, however far out that is. All right, but look. If it's in a circular orbit, what's its velocity? Well, it's right here. So if I square this, v squared is just equal to gme over r. So I can put that in for v squared. So the total energy is equal to 1/2 m times gme over r minus gme times m over r. Both these are the same r. That's the radius of the orbit. Stay with me. Go down here. Look, these have in common a gmem over r. So I'm going to pull that out. So I have gme times m over r times 1/2 minus 1. What's 1/2 minus 1? -1/2. So this just becomes the total energy in the orbit is minus gmem over 2r. Or gmem over r is the potential energy. We can say, oh, so really this is just it's just the potential energy, which already has a negative in it, divided by 2. So the total energy in a circular orbit is just the potential energy divided by 2. Like that doesn't make sense. It does. And if you have a rocket in orbit here, and you want to go from this orbit to another orbit up here, what do you have to do? You have to change its energy. And so that's how they calculate and say, okay, I have to change its energy. To change its total energy, I have to do work on it. And so how do you do work? Well, you apply a force through a distance, and the force is the rocket thrusters. That's what rocket scientists do. It's not as complicated as they make it out. You just got to change the energy of the orbit, and that'll put it in different orbits. Change the radius. Okay? Number u is the radius of the orbit. So if I want to make this bigger, I have to change the total energy. You're not going to change g, or the mass of the Earth, or the mass of the rocket. Well, the mass of the rocket changes when you burn propellant out, but not much. But you do change r. All right. So far, so good. Let's talk about angular momentum in orbits. So, angular momentum in orbits. I already mentioned earlier that angular momentum in an orbit is conserved. So let's say we have an orbit like this. Here's the sun. And we have something that goes in a fairly eccentric orbit. Remember from our definition, over here is that perihelion. Closest to the sun, when it's out here, it's at aphelion. Okay. Now, a few more things. We have this distance from the sun. We draw from the center of the sun to the, whatever it is, on this case, a planet or comet or whatever. We call this the radius of aphelion, or RA. That's how far it is away from the sun when it's furthest away. And over here, this distance from here to here, this is the radius of perihelion. But remember, the total of that, as long as they're at perihelion and aphelion, the total of that is the major axis. So if I add those together, I get the major axis. But remember, I don't care about the major axis. What I want is half of the major axis, or the semi-major axis, which is A. So this becomes equal to 2A. Remember, if I draw my line here, this distance is A. This distance is A. So if I add up those two distances, they equal 2A. Why do you need to know this? Well, if you know this distance and this distance, you can figure out what A is, and if you know what A is, you can use Kepler's third law.